Okay, we're going to do another related rates problem here. And this one has to do with some cars. So let's say we've got a red car traveling west at 50 miles per hour. Again, as I read these questions, I like to take notes on what's going on. Sort of helps me organize my thoughts. So maybe since it's a red car, I'll highlight in red. The red car is going west at 50 miles per hour. And there's a blue car traveling north at 60 miles per hour. Both are going towards the same intersection, two roads. At what rate are the cars approaching each other? So that's what we're being asked. So at what rate are the cars approaching each other when, that's going to be important for us later, when the red car is 0.3 miles from the intersection and the blue car is 0.4 miles from the intersection. All right, this is one of those problems where sketching a picture helps a lot. So in other videos I've done, we had like shapes, like a sphere and a cylinder, and maybe sketching like wasn't super helpful. Maybe it was a little helpful, but not like totally necessary. Here, I really need to sketch out what's happening because it's hard for me to think about it right now. Well, I know I've got like, let's see, here's my little sketch. I can write nicer than that. Here we go. Here's my little sketch. I've got an intersection. I don't know, let's say it looks like this. Let's say here's my intersection. Okay. And the cars are approaching. Maybe I shouldn't color it in because I'm just going to make it harder to see. You don't have to care as much about your sketches as I do right now, so. But I do want to make it look like a little intersection. Okay. There's my little intersection. And the cars are approaching the same intersection. So they're going towards this where it's crossing here. We're told that the red car is traveling west. So let me draw a little car here. Here's my little car. Kind of looks like a turtle, but there's my little car. It's going west. My red car going west at 50 miles per hour. And I've got a blue car going north. And I know, like, maybe it was a little confusing. How do I know the red car is over here? Like, why isn't it over here? Well, I know it's over there because it's going west, like we're told it's going west, and towards the intersection. If I had drawn it over here, like if I had drawn it, a little car over here, and it was going west, it'd be going away from the intersection. So, and if I had drawn it over here, it'd be going off the road, right? Okay, so I know it's over there. The blue car is traveling north at 60 miles per hour and going towards the intersection. If I try to draw the blue car here and going north, well, it's going off-roading. If I try to draw it here and it's going north, it's going away from the intersection. If I draw it over here, still off-roading. So I know it should be down here. So my blue car, or my little turtle, because I'm not very good at drawing, my blue car is going north at 60 miles per hour. And we want to know what rate are the cars approaching each other. Now, I view this approaching each other as like the distance between the two cars. The distance between the two cars is that distance, this kind of like they're both getting closer to each other this way and closer this way. So this distance here is getting smaller. Okay. So that's my little picture. It gives me a little more clue about what's going on here. Let's move on to the rates portion of our acronym. And when we write down our rates, we need to start giving variable names to stuff, because in this problem, there's no variables that we're told specifically to use. So we just get to make them up. I'm going to use X, Y, and Z. You could use A, B, C, or like, actually, maybe A and B is better. I don't know. Since we have a red, that's okay. I'll use X, Y, Z. No need to change it right now while I'm making the video. So let's say the quantities that I know, I'm really interested in like the position of the cars, like how close they are is the position. I also know a miles per hour, which is like how a position per time, that's a velocity. So let's say that X is the position of the red car. So if the red car gets a position name, so does the Y car. Let's say Y is the position of the blue car. Okay. And I know the velocities of these cars. I know that dx dt, that's the velocity of the red car. I know the red car is going 50 miles per hour. It's going 50 miles per hour, but the cars are getting closer to each other. So the distance between them is getting smaller. So I'm going to make this a negative. Distance between the cars is getting smaller, so I'm making that a negative. If they were positive, they'd be getting farther apart, right? But they're getting closer. So similarly, dy dt, I'm told the velocity of the blue car is negative 60 miles per hour. And again, I made this negative because it's getting closer. These are getting closer to each other, so this distance between them will be getting smaller. Let's say I want to know something about this like green line here. So let's say Z is the distance between the cars. And I want to know what rate the cars are approaching each other. So I want to know what's the rate of this distance. So here, dz dt is what we want to find. Okay. So maybe I'll say like, this is X, this is Y. So this little car here is X, this little car's position here is Y, and this distance here is Z. Okay. So again, this one's a little more complicated than ones we've seen because we had to sort of make up names for stuff. We had to give names to these positions and kind of work out what's important and what's not important. I guess maybe even more descriptive than position of the red car. Maybe I should say this is the distance from the intersection. So say this is red car distance from the intersection. That might be a little more clear about why their derivatives are negative, because the distance from the intersection is getting smaller. Yeah, I like this better. Okay. So distance from the intersection of the red car is getting smaller, so their derivative is negative. Distance from the intersection of the blue car is getting smaller, so the derivative, the derivative of that is negative. Okay, we've got our sketch, we've got our rates. Now we need to write down an equation. Let's take a look at our picture here. And our sketch looks like a triangle. We have like sort of the sides of the triangle as well, and we've got like this hypotenuse. So let's write down the equation of a triangle. I'll sort of put it next to my sketch so you can see how I'm getting that. And you know what? I don't need those parts of the intersection really. So here's my sketch. Oh, that's not great. That's pretty good. Okay. We'll go with this picture. So I have, here's the position of car B, or how far away it is from the intersection. Here's the position of car A. So I have Y is like this distance here, X is like this distance, here's the intersection. And then Z over here is like the distance between them. This is what I had in green. earlier. Okay. So my equation that relates these things is Pythagorean's theorem. I'll go ahead and, this is a right triangle. So I know that x squared plus y squared equals z squared. These are the legs of the right triangle, and this is the hypotenuse. So I can write down an equation relating those things. Great. Now I can take derivatives. And again, as always, these are derivatives with respect to time. So every time I take derivatives of things that depend on time, like this position from the intersection changes as the car moves. This position changes as the car moves. And this distance, if the red car ends up here at some point and the blue car ends up here, then that distance, this is z, is also getting smaller. So whenever I take derivatives of these variables, I need to write d variable dt next to them. Okay. So the derivative of x squared, I take the derivative as usual. So I'd get 2x, but x depends on time. So I put dx dt next to it. Plus the derivative of y squared is 2y. But again, I got to put dy dt next to that. And the derivative of z squared is 2z. I put a dz dt next to that. Okay, great. Now, we're really at the when stage of our acronym. Remember, maybe I didn't point to it too much, but I had my little SREDWU. We did the sketch, we did the rates, we did the equations. Now we're at the derivative. Nope, we took the derivative. Now we're at the when. Okay. Okay, if you wanted to, there's a 2 on every one of these terms. So if you divided both sides of this equation by 2, all those 2's would cancel. You can do that. I'll not do that just so I don't lose anybody while I'm doing this, but you could do that. It's totally fine. Okay, so our when, let's go back up here and remind us of the question, is when the red car is 0.3 miles from the intersection, so that's x, and the blue car is 0.4 miles from the intersection, that's y. Okay, so back down here at the when, it's when x equals 0.3 miles and y equals 0.4 miles. We were told dx dt and dy dt, we're looking for dz dt. So this one we've got, x we know, y we know. Dx dt we were told this was the constant, we decided was negative 50 miles per hour. So that quantity we have. We know dy dt. Y dt was negative 60 miles per hour. So that I know. This is what we're trying to solve. So I still need to plug in a value for z. Because that I need that to be a number because I'm trying to get dz dt equals a number. Okay. So let's figure out how we could do that. What's z? Well, I'm going to argue that we can figure out what z is because we know what x and y are. And we have this equation that relates x, y, and z. This equation is always true, so we can use it. Well, we know x squared plus y squared equals z squared. And we're given that x is 0.3 and y is 0.4. So we just need to figure out what z is in this expression. So I'm going to plug in 0.3 for x, 0.4 for y, and solve for z here. Okay. So 0.3 squared is 0.09. 0.4 squared is 0.16, and that equals z squared. So I need to take the square root. So this is 0.25. So I know z squared equals 0.25. I need to take the square root of both sides. Now, normally I would say z equals plus or minus the square root of 0.25. That's plus or minus 0.5. But because z is a distance, it's a length between the two cars, I'm going to take the positive value because I don't want to, I can't think about a negative distance. I'm going to think about a positive different distance. So I'm going to say z is the positive value, 0.5. Great. Now I have a value for z that I can plug in up here when I'm solving for dz dt. Okay, so I have, let's plug in our values. I have 2 times x times dx dt. So I'll indicate what this was. This was 2x dx dt. I'm just plugging in the numbers now. Plus 2 times y dy dt equals 2 times z dz dt. I'll just do the whole thing. Equals. Okay. At this point, you need to solve for dz dt. Now, I'm not going to do all the algebra on the screen here, but really you're computing dz dt. I'm trying to get dz dt by itself. So I'm just going to divide both sides of this equation by 2 times 0.5. I'm dividing this by 2 times, 0.5, and I'm dividing all this by 2 times 0.5. Okay, so I'm going to compute 2 times 0.3 times negative 50 plus 2 times 0.4 times negative 60 all over 2 times 0.5. And if you put that in a calculator or you just kind of spend some time writing it all out, you'll get negative 78. Okay, negative 78. Our last part of our acronym is the units. So dz dt equals negative 78. Z, this distance between the cars, is in miles, and time in this problem is in hours. So this is miles per hour. And this is our final answer. And you'll notice that this is a negative rate because the cars are getting closer together. Okay, that is it for this problem. Let me know if you have any questions.